Hello, my name is Belén Planes. I'm in the last year of my astronomy PhD and I work in CIMAP group in Mendoza, Argentina with Dr. Millán and Dr. Bringa and in a strong collaboration with Dr. Urbasek from Germany. Today I will present a work titled Collision between granular micro-aggregates, condition for dust agglomeration. Collision between dust aggregates are important in many astrophysical scenarios. In planetary formation, it is crucial to understand how a system evolved through collisions, as it is currently unknown how dust aggregates grow to form planetesimals and, eventually, large bodies like planets. The results of a collision between dust aggregates depends on the material properties of the grains that make up the aggregates and the impact velocity. Both quantities are integrated into most current models, but also the properties of the aggregates as mass ratio and filling factor could change the results of the collision, and these effects are poorly studied. This image shows the temporal evolution of a system with same properties of the aggregates, but on the left side, the projectile have double of initial velocity than the projectile of right side. So obviously the impact velocity is an important factor. Here you can see a total fragmentation of the target in opposition to this case where there is a craterization and adhesion of the projectile to the target, with a few particles ejected during the process, generally called SP or sticking by penetration. We study how variation in the impact velocity but also in the porosity and the mass ratio between the aggregates affect the results of the collision. Also, we are interested in the threshold values that separate agglomeration from fragmentation. The interaction between aggregates of dust formed by hundreds of thousands of individual grains of spherical silica of radius 0.76 microns will be studied by numerical simulations. We use the package lamps and our aggregates are built follow the ring model, whose reference is here. Then, the force involved during collisional process are based on Dominic and Tillens, but with improvement related with incorporation of friction, making this model more realistic. The 3D figures that I exhibit in this presentation have been obtained using Obito. Now we are going to summarize the impact of parameter study by us. In this first row, I show the initial state. The first two pictures are aggregates with same filling factor, 0.15, but different mass ratio. The first 10 and the second 60. And these two pictures show aggregates with same mass ratio, but different filling factor. The last one has 0.40. Now we will evaluate the outcomes. We can observe that porosity has a crucial role. For the same impact velocity and mass ratio, for more compact aggregates, we observe this outcome, similar to petal structure. But for more porosity aggregates, we observe this result, similar to a piston effect. Both outcomes were explained in our recent work. The reference is here. On the other hand, the impact velocity obviously has an important effect. Same aggregates but different impact velocity show that in this case, with a velocity of 25 meters per second, a big crater is observed. But this velocity is not enough for breaking the target, where we show a slice of 20 microns wide in order to show that the velocity gradient is too slow that this material won't be able to break out. But for high velocities, the behavior is fragmentation. At last, if now mass ratio change, for the same porosity but even with a lower impact velocity, we observe that target is fractured. These results are near to center published. As all dust aggregates in protoplanetary disks likely do not have the same mass ratio and porosity, we consider that building an improved model that takes these parameters into account will be very important. Our results until here give a much more positive scenario for the formation of large bodies by collision processes. Here we distinguish two possibilities. After the collision, the projectile penetrates and fuses into the target with low erosion, so target gains mass and growth. The other case is that the target loses mass due to fragmentation or if a large erosion occurs during impact. An interesting relationship could be established between the initial energy of the system and the resulting regime. If we plot the impact energy as a function of the initial filling factor, we find a linear relationship that separates the regimes very well for all mass ratio and velocity studied here, but with two exceptions. Intermediate values of filling factor between 0.22 and 0.30 result in growth at higher energy than expected ones. The explanation is the transition between the piston structure and the piston effect that take place at these intermediate values of filling factor. And for filling factor 0.15, there are some mass loss events at lower energy than expected. Finally, we show a complete image with all results we have. This figure represents the number of total ejected particles normalized to the total number of particles in a system. It means number of particles in projectile plus number of particles in target, as a function of filling factor. Shapes are for mass ratio and colors are for initial velocities. So, if we have more ejected particles than particles in projectile, the target loses mass, and this line represents this threshold for both cases, mass ratio 10 and mass ratio 60. The dot under the line indicates growth in each case. From this figure, we can estimate the minimum velocity necessary for the loss of mass, VL. We observe that this velocity VL increases with the mass ratio, as one could expect. If we focus on high mass ratio, here 60, again intermediate values of filling factor may allow growth at higher impact velocities, as higher as 100 meters per second according to green squares. And for this value of mass ratio, all cases showed mass gain for velocities up to 50 meters per second. Then, if mass ratio has a value of 10, the situation changes, and this velocity VL has a maximum possible value of 25 meters per second, these pink circles. And for all filling factor studied, we observed growth only if V is less than 10 meters per second, these orange circles. Well, some conclusions of our work are: variation of filling factor and mass ratio have a large impact on collision results. The incorporation of friction in our model allows agglomeration at higher velocities. The critical velocity VL increases with the mass ratio. And for high mass ratio, largest growth appears for aggregates with porosities between 65 and 80%. So, thus growth due to collisional processes could be more feasible than in previous estimates. Now we are building a Monte Carlo code. Based on our results, we start with a big number of aggregates with different porosities and size, and the system will be evaluated after a given number of random collisions. That is all. Thank you very much for your time.